So, how would we persuade a donut to behave like this? Well, we'd ask it nicely. But before that, we'd have to know quite precisely what we were asking our donut to do, and to build our donut in such a way that it could definitely understand our requests. How would we do this? By building and animating our donut in geometry nodes. Let's get started. Okay, how would we go about modeling a donut in geometry nodes? Let's start with a torus. Let's get rid of the group input. To make a torus, let's start with a curved circle. Let's plug it into the output. This is the major radius of the torus. So what we want to do is to sweep a smaller circle, or a minor radius, around this one, which is easy enough. Let's get a curve to mesh node. Put it there. Let's duplicate this curved circle and plug it into the profile curve. Now this is supposed to be the minor radius, so let's make it a bit more minor. Something like that. Great. Now there are donuts which look like this. It's not quite the kind that I'm going for. So up here, I'm going to add a Bezier circle, a curved circle, move it across so I can see it. And I'm going to scale it down so it's roughly the same as the minor radius. I'm going to go into edit mode, subdivide it, and just bring in these side handles a little bit. Just this kind of thing. The whole process is non-destructive, so you can always come back and change this later if you want to. I'm going to scale it out on the X a bit. That should be okay. I'm going to apply the scale. Back in my geometry node, I'm going to bring in the custom profile I've just made, set to original, and plug it into the profile curve instead of the curved circle. And there we go. I think we could do with a bit more radius, a bit more resolution. So let's pump this one, the major radius, up to 128. And let's increase the resolution on the custom profile by adding a resample curve node set to, I think 60 should be enough. Right. Now you'd have no reason to suspect that this was going to happen, but if we examine the face orientation, we'll see all of the normals are backwards. I don't know why this is happening. If we use a native curve circle from geometry nodes, this doesn't happen. If anyone could tell me why this happens, I would be very grateful. Anyway, the fix is easy enough. We just get a flip faces node and stick it here. And we can see the normals are as they should be. So turn off face orientation. Right, why have we built a donut like this? Well, there's no torus mesh primitive inside geometry nodes, but even if there was, we wouldn't want to use it because all of the animation we're going to do, all of the twisting, will be based on adjusting the curve tilt of the major radius. So get a set curve tilt node. We see if we increase this value, the whole donut is tilting round. It's not twisting yet. This is just a tilt. A twist happens when the tilt varies around the radius, and we'll get to that later. But for now, let's set it back to 0. All of the modeling of the donut is going to be done over here in Meshland. All of the animation of the donut happens over here in Curveland. So rather than just move on, there are certain really important things we need to capture. So let's get a capture attribute node. Let's plug it in after the major radius, duplicate it and plug it in here after the resample. And what we're interested in is the factor, or the spline factor. So let's get a spline parameter node and plug the factor into the value on both of these capture attributes. We need to store this information over here in Mesh World. So we need 3 store named attribute nodes. Okay, let's duplicate this, and again. Now the first two are floats, so that's fine. The third will be a vector. So what we want to capture is the spline parameter, or the factor of the major and minor radiuses. So let's call the first one major, let's call the second minor, and let's plug in this attribute from the capture to the major and from the minor to the minor. Now I'm not going to go into materials in this tutorial. Between modeling and animating the donut, it's already going to be quite a lot, but I will show you how to get possible UVs to texture it with. So let's call this third attribute DUV for donut UV. Let's get a named attribute node, and for this one let's get the major, duplicate it, and let's get a minor. Let's get a combine XYZ. Let's plug major into X, minor into Y, and the result into the value on our DUV vector. To get it out into the shader editor, first of all we'll need a material, which I'm going to call base because it's the base of the donut. Get a set material node here, this is essential, assign base, and if we go over to shading, okay, we get an attribute node. Geometry is fine, the attribute was called DUV. Oop, thank you, my V key went on strike. A good texture for diagnostics is a checker texture. So let's plug from the vector into a checker texture, have a look at it, maybe increase the scale a bit. And this should be checkers. We can see that on the major radius, this is slightly elongated. They should be squares. We can deal with this with the mapping node. If we scale either the X or the Y, I'll try the X, scale it up to about let's say 2.5. We're just looking for squares. If we now use this vector, this output, as the basis or the texture coordinate for any texture, then that texture will stick to the donut. It's, like I say, these are passable UVs. These are not clean UVs. They, on the seams where 0 gets to 1, we have this problem. Bit of a classic. There are fixes for this. I recommend looking up Intagma's videos on procedural UV unwrapping. I'm not going to go into that. We don't have time. And for most cases, these will be good enough UVs. Point being that if we tilt our donut, we can see the texture sticks to it. This wouldn't happen otherwise. Okay. While we're here, there's a kind of an important number which I have to explain. If I don't, some of the maths in a later section will seem really mysterious, so I'm just going to explain it here. Let's get a, well, you don't have to follow me, but watch this. Let's get a viewer node on the geometry after DUV, and what we want to see is the minor radius. It's a spline parameter, so it goes from 0 to 1, 0 being black, 1 being white. So it starts and ends on the sort of inside middle of the donut. The important number, or the thing to remember, is that at the kind of crown of the donut, at the very top, that is 0.75 on the minor radius. We're going to need that later. If, while you're making your curve profile, you've rotated it for some reason, or rather if you've rotated it and then applied that rotation, this will be off. And I'm not going to say that it won't work, but the numbers will all be wrong. So if you want to follow me, then make sure your minor factor is running like this with 0 to 1 on the inside and middle. Okay, don't need that anymore. Okay, what I would recommend doing is take everything from flip faces to the third store named attribute, and let's put them in a group. I'm going to call this group base, because it's the base of the donut. I would make sure the set material is outside this group, because we're going to be using this geometry to derive the geometry for the icing and then the sprinkles, and we would like to set those materials separately. So, if you're not interested in icing or sprinkles, or you're impatient, or you're a coward, or whatever, all of the animation will work from this point, so you can skip ahead. As I said, all of the animation will be done with this, or all of the twisting animation will be done with this set curve tilt. And we're going to want to keep referring back to it as we model the icing and the sprinkles, because we're going to want to stress test our donut and make sure that it can withstand all of this kind of thing. So it's a good idea just to move the set curve tilt node up, just so you can easily refer back to it. Okay, let's put this back to 0. Okay, let's make some icing. How would we do this? Well, first let's make some space over here. You may have done this before, and the way you probably will have done it is you just copy the top faces of the donut and solidify them and go from there. Okay, let's do that. So let's take our base donut geometry into a delete geometry, because we'd like a copy of it, but we want to delete the bottom bit. And then how do we do that? Well, we get the position, specifically the Z position, so separate X, Y, Z, and we take the Z into a less than node, and we could say, let's delete all the geometry, I don't know, below about 0.2. So less than 0.2 into the selection on the delete geometry. We'll need to see this thing, so let's add, let's add a join geometry and stick this into here. You can't really make it out, but in any case, we would like to extrude it, so, or solidify. So let's extrude this mesh. That's not quite what we want. So let's uncheck individual and bring the offset scale down to, I don't know, about, let's say 0.05. That's okay. And you might be thinking, great, okay, that's a good start. However, if we go back and adjust the tilt, we'll see the icing isn't following the donut underneath it. It's just kind of surfing on the top. And of course it is, because this is exactly what we asked it to do. I wasn't being entirely facetious in my introduction when I said we have to ask it nicely. Okay, what does that mean? Well, okay, for a start, let's reset the tilt. We can't use the Z position, because the Z position has no idea about the curve tilt. However, we can use our minor radius. So let's get a named attribute. And we want the minor. Now, if you recall, this point, the crown, the middle of the crown, or the apex of the minor spline factor was 0.75. Okay, so we can say we take the minor attribute into an equals node and say where the minor attribute equals 0.75 with a certain epsilon, which is a range on either side of it. I'm going to say 0.2. Now, This will be the icing that we want to keep, so we have to tell this delete geometry to get rid of everything else. So take this into a Boolean math not node and plug this into the selection instead of the Z position thing. And now, if we play with the curve tilt, we'll see, hey, the icing is sticking to the donut. That's fantastic. Okay. Tastes vary, as do donuts. You might want more icing than this, or probably less icing than this. The epsilon will determine how much icing you get, just so you know. But I'm going to go with about 0.2 because I want it sort of hanging over the edge a bit. All right, it's a good start, but this is, it's a bit straight. It's a bit mathematically perfect. We don't want that. We like nice, drippy, undulating icing. How would we do that? Well, we want it to wobble. And how do we wobble anything in geometry nodes? We use a noise texture. Okay, we know that we don't really want the noise displacement to affect the thickness of the icing. So let's do some kind of noise displacement before the extrusion. I might need a bit more space here. So let's get a set position node. Let's get a noise texture. Oop, not like that. And let's do what we almost always have to do in geometry nodes when using noise texture. Let's subtract 0.5 from each axis to center it. And then let's chuck it through a vector math scale node to give it some control. And if we plug it into the offset on this set position, it looks awful. Okay, of course it does. First things first, let's bring down the scale a bit. Let's take all the detail off the noise, and let's bring the scale down something like that. Okay, well, it's obviously, not good enough, but what are the problems here? Well, it's displacing in every direction, so it's going off the donut and it's clipping into the donut. That's no good. Okay, so we need to slightly qualify the noise texture. What we want is noise, but only on the edges of the icing. How can we do this? Well, by creating a kind of mask. Okay, let's get rid of this. We don't need it. How would we do that? Well, let's get a copy of our minor... no, not that. Let's get a copy of our minor attribute. We know, as I said, at this point, the apex of the top is 0.75. We know that this bit at the side would be 0.5, and we know that on the inside, where the seams meet, it will be 1. So 0.75 minus 0.5 would be 0.25. 0.75 minus 1 would be negative 0.25. So if we can just get rid of the sign, the positive or the negative, we'll have a gradient effectively running in both directions. So let's do that. So let's get a math node, and we want 0.75, our apex, subtract the minor radius, and then we want to put this in through an absolute so that we get rid of the sign, and now effectively we have that gradient. If we put, we need a bit of space. Crikey. If we put this absolute through a map range, we can use it to map the amount of noise we want on the donut. So from 0 will be 0.75, to a certain amount, let's say 0.3, and we want minimum noise to be 0, maximum to be about 0.5, let's say. If we do this from 0 to 0.3, it will start. The noise will start almost immediately. Let's have the noise start a bit further out. Let's say 0.1 to 0.3. So we just plug this into the scale, and then plug that back into the offset on the set position, and great, we can see it's not happening at the top and it's happening on the edges. However, we have another problem here, which is that the icing is kind of hanging over the edge in a slightly, unsatisfactory way. And you'll find somewhere or other that maybe if we tilt the donut, we could see this better. You will find, okay, there's a bit, as well as hanging over the donut, it will clip into the donut here and there. We can do better than that. So let's reset the tilt to 0. Okay, how to make the icing hug the donut. What we need to do is just to stick it back onto the donut. How do we do that? We use a raycast. So from our base donut, let's take out a raycast with the base going into the target geometry. Okay, how do we get it to stick? Well, we have to ask it very nicely. We have to say stick to the nearest point. In order to really tell it to do that, we need to find the vector in question. To do that, we'll need a sample nearest surface. There we go. And we'll set this to vector. And what we're interested in is the position. Let's plug this position into the value. So this is the nearest point on the donut for every point on the icing. If we take this and subtract the position, which in this context means the position on the icing, then we get for every point a vector pointing towards the closest point on the donut. In other words, the ray direction. So we plug this into the ray direction. We do not need 100 meters worth of ray length, and if this is too long, it can cause certain kinds of glitchiness. So I found it's best to put this to about 0.1 meter, assuming you're using the same elephant scale that I am for this. Right, we need to do this operation after this noise displacement set position. So we'll need another set position. If you've ever played with a raycast before, you might know that under certain conditions, like if a ray can't find a point on a target geometry, it will just teleport to the world origin, causing some hideous glitching. So to prevent that happening, let's limit the selection on this second set position to the is hit. So this will only be in effect if it finds a point to hit. And we just plug the hit position from the raycast into the position, and we'll see that, okay, we've only got the wobbling on the edges, and it's also hugging it perfectly. And let's just test. Okay. There's a slight bit of glitchiness over here, but otherwise it's not too bad. Hang on, maybe if I adjust the ray lengths, I'm going to have maybe a slightly longer 0.15. That dealt with that. And where am I? Back to the tilt. You're going to want to use this this tilt as a stress tester. You adjust your values, find some icing, some drips that you like, and then do this to make sure there are no glitches. As a general rule of thumb, if your donut can endure this tilting without breaking, then all of the later twisting animations it will be fine for. Okay, so there's one point, and it's a bit subtle, but right now the noise field, which is causing the kind of dripping on the icing, is working in world space, so it doesn't keep its shape like the edge of the icing. It's almost kind of more liquid, like it's kind of dripping into these different positions. And you might like that, and you could use that. But another way to work, and this might be a bit more stable actually, is we can make the icing keep the shape of its drips by, instead of just using default world space coordinates for the noise texture, if we get another named attribute, this time the major radius, if we use this as the vector for the noise texture, and then we're going to want to scale this up quite a bit to, I don't know, I think about 6.9 can work well. You will find if you're using the major radius as this vector, you're going to get this kind of thing. This is the seam where 0 meets 1, but you know, you can find points where it's kind of undetectable. Like, now I'm just going to say 6.9. And now, if we do our tilting, oops, we'll hopefully see that the icing kind of keeps its drips. You know, this is really a matter of taste, so it's up to you. But I encourage you to experiment with this and keep tilting it just to make sure it doesn't break. The reason, if it's going to break, it's going to break because of the raycast. It's generally quite a solidly built donut, but this node is the most temperamental in the whole setup. It's very easy to break it. So if you use too much noise, for example, I can just demonstrate. As you can see, things will break. And it's possible that, you know, you'll find some noise. If you want a really drippy donut, you'll find some noise that looks okay here, but then, you know, it will break when you tilt it. So just be sure to keep doing that. And if it doesn't break here, then it will be solid later. Okay, I'm going to put this to 0.6. Right. Okay, this is a bit of a mess. How am I going to do this? I am going to connect all of these and move these because I want all of this stuff, everything everything after the base and before the join geometry, excluding this line with the set position, set material, I would like to be in one group. So let's select it, this too, and Control G to group. And I didn't do that right, did I? I totally... Okay, let's try that one again. No, I don't want you. I just want you lot. And that's better. And this group, let's call it Icing. And once again, if you want to set a material for the icing, I recommend doing it outside the group here, and the DUV attribute, the UVs that we made here, will propagate through onto the icing mesh, so you can use the same process to use UVs for some kind of material. Alright, onto the sprinkles. Okay, sprinkles. Well, you might be thinking this bit should be easy at least. Well, yes and no. All we need to do is distribute some points on the icing and then instance the sprinkles on the points, and yeah, okay, let's try that. So let's take the icing into a distribute points on faces, and let's, so we can see it, put these points into our join geometry. Okay, and maybe, increase the density. Okay, it looks all right so far, but if we adjust the tilt, you'll see points are kind of zipping in and out of existence randomly. We do not want our sprinkles to be doing this. We can do a lot better than that. So rather than use a distribute points on faces, let's, how do I do this? Get a mesh to, no, what is it? Mesh to points, yes. A mesh to points node. And plug that in. Okay, this is a bit ridiculous, of course. But if we now get a delete geometry after the mesh to points, and for a selection, get a random value set to a Boolean, and put the probability of deletion quite high, plug this in, then we'll find, okay, that's looking all right. And now, if we tilt the donut, we'll see the points are sticking. They are not piecing in and out of existence in that infuriating way. So, that's the start. However, these are kind of just going everywhere randomly. We want a bit of weight painting. We want there to be more sprinkles on the top than there are on the edges. How do we do that? Well, in a similar way, in fact, an identical way to the gradient we created for the noise texture, we can get our named attribute minor, and once again, to get the gradient, we get a math node, set it to subtract. We'll say 0.75, subtract the minor attribute, and once again we'll send this through an absolute, so we get a kind of symmetrical distribution. And if we plug this into a map range, and again we want to go from 0 on the apex to, I don't know, maybe like point. This will depend actually on how much icing you have on your donut, so you're going to have to tailor it slightly. So let's go from 0 to 0.15, and at 0 we would like there to be a low probability, so, or a high probability of deletion. So let's say 0.9, and at the edges we want a total probability of deletion, so 1. Okay, so let's plug this in to our selection, and it doesn't work at all. What have I done wrong? What have I done? Oh, of course. Okay, this goes into excuse me. This goes into the this map range goes into the random value, and that goes into the selection. And now we can see, okay, we're getting some sprinkles on the top. If we'd like more sprinkles on the top, we would take the 2 minimum down. That's probably too many. And if we want them a bit further out, we would take the from max up a bit. Okay. I think there's too many. Okay. I'm going to say that's fine. All right. And now the sprinkles themselves, which we'll want to instance on these points. I'm not going to insult you with a remedial sprinkle modeling lesson. If you've got this far, you probably know how to do that. So here's some I made earlier. All I will say is, just to get the numbers right, make sure they are oriented this kind of a way with the rotations applied. And put them in a collection, of course, called sprinkles. And I'm going to bring in my sprinkles collection, separate the children and reset the children, get an instance on points node on here, and plug the instance into the instance and click pick instance. And they're way too big, so scale them appropriately. I think about 0.2 should be all right. Okay, now we need to sort out their rotations. Because we're not using a distribute points on faces node, we don't conveniently have access to the normals, but we can get it from here, from the icing. So let's get a sample nearest surface node. Sample nearest surface. This, okay, again, we want a vector. I'm worried. I'm worried about that, so I'm just going to move it. And what are we after? The normal. So normal into the value, and we would like to align this normal to the z. So let's take this through and align Euler to vector, put it into the vector input, and z here. We put this into rotation, and we'll see they're all rotated appropriately. They're all sticking. However, they're all flying this way. So let's use a rotate instances node here. And what we want is a random rotation on the z. To do this, very easy indeed, we just get a random value, and a float is fine. And we want to go from in degrees language, we want to go from 0 to 360 degrees. And you would be forgiven for thinking that because this has degrees here, it would take an input in degrees. It doesn't. It takes inputs, all of the geometry nodes which have, alleged degrees in them, take inputs in radians. 360 degrees in radians is tau, or 2 pi. Make friends with tau. By the end of this tutorial, you're going to be best friends with tau. So we want 0 to just write tau, which is 2 pi, and then we want this on the z, so into the z on a combined x, y, z, and plug this into the rotation. Now they're rotated randomly. If you don't like this rotation, you can change the seeds. Also, if you don't like this distribution, you could change the seed here. And let's do a quick check that everything's tilting okay. Yep. No sprinkles disappearing. Fantastic. Okay, all we need to do now is take all of this business, everything after the icing, excluding these lines, put it into a group, call the group sprinkles, and now we can get to the animation. Mobius twist. We're starting with this one because, believe it or not, it's actually kind of the easiest. Back over here in Curveland, let's go to our set curve tilt node, and let's make it its own group. Let's call that group Twister. Now, we don't want the selection or the tilt to come in from the outside, so let's get rid of that. And, in fact, let's just get rid of them entirely. Okay, we know, from experience, that if we just move this, we're adding a constant value, so the tilt is the same all the way around the donut. In order to get a twist, we need the tilt to vary. How might we do this? Well, let's try using a spline parameter. Let's just take the factor from 0 to 1 into the tilt. Again, like the rotate instances node, even though it looks like it's taking degrees, this input accepts radians. So this is tilting from 0 over here to 1 over here. This is 1 radian's worth of tilt. And of course, because it's discontinuous here, we get this really ugly seam between them. How can we deal with this? Well, how about, instead of going from 0 to 1, we went from 0 to a full tilt. What would a full tilt be? 360 degrees, or in radians, tau. So let's take our factor, put it through a map range 0 to 1 to 0 to tau tau, plug it into the tilt, and there we go. Yeah, it's quite handsome, a kind of Mobius donut, infinite donut. What about if we would like to tilt it, having twisted it? Very easy. Just get a math node and just add value to it. And what happens here is we're now just adding a constant again. So it's once again it's tilting all the way around the donut, but having been twisted in advance. What if we wanted a kind of infinite loop animation, like an infinite loop of an infinite donut? Well, let's give ourselves, I don't know, 50 frames. Let's get let's get a scene time node. Let's take the frame output into another map range, to the value. And we want to go from frame 1 to frame 51, so the frame after the last frame, just to make sure it loops cleanly. And we want, how much do we want here? Well, let's do one full rotation. What would that be? It would be tau. Great. We plug this in, and if we press play, we'll see with our 50 frames, we've got a looping animation. While we're here, this I guess you could call a Mobius or infinite donut. This is one twist. How about if instead of going from 0 to tau, we went from 0 to 2 tau? We'd get this kind of thing, which I don't know what to call it really. Maybe a yin-yang twist, it kind of looks like. And of course, you could see how easy it was to do that, and you can play around with these numbers. If you don't have multiples of tau, let's take an arbitrary number like, I don't know, 10, you will get this discontinuous point, which I think looks horrible. So, just beware that tau or multiples of tau are kind of the happy numbers to use because they loop round. Okay, this isn't bad, but what if we wanted to do a kind of formation effect from a normal donut into the Mobius donut? Okay, it's a little trickier, but not super tricky. Okay, first things first, let's remove this tilt and take this back to 0. And I'm going to give us a few more frames to work with. I'm going to go for 120. What if we get another scene time and bump it into a map range? Oh, I cannot spell today. And let's say we want from frame 1 to frame 20, we would like to go from a normal donut to the Mobius donut. If we put from 1 to 20, from 1 to 0, if we now put this into the from min on this map range, we'll see that we go from donut to Mobius donut. I'll confess I'm not super happy with this transition. I think at the beginning this is really ugly, that little jagged bit, but it'll only last a frame or two. There's probably some trig genius out there who can think of a much more elegant way of doing this, but this is what I'm doing. So what if we wanted it to form like that and then do a twist? Well, okay, it finishes forming at 20, so why don't we say from frame 20 to, I don't know, frame 80, we would like to do one full twist, tilt. There we go. And it stops a bit abruptly. If rather than using a linear map range here, we use a, let's say, smooth step or smoother step, it's kind of the equivalent of a Bezier interpolation in a graph editor. So it should, instead of just stopping abruptly, it should kind of break, yeah, like that. Alright, what if after it stops we would like the donut to go back to a regular donut? All we need to do is to make a duplicate of these nodes, get another add, and this time, okay, well, let's get the frame range first. Okay, let's say from 80 to 100. This time we want to go not to tau, but to negative tau, because we kind of want to unwind it. So 0 to negative tau, and we add this and go to the beginning. So we form, do a tilt, and then unform. Okay, and you can, play with these values. I think maybe it would look a bit nicer if we start the tilt earlier and end a bit later. So we're, I don't know, maybe as much as 95. So we're still tilting when it's unforming. Okay. Right, just to look at, if you come back to this, it's a bit, it's not easy to tell what's going on here, so I'm going to frame up this stuff just so you kind of have a, I don't know, a bit of a clue. So I'm going to call this first group, I'm going to call form for the formation. This middle, what am I doing? Yes, I will call tilt, and then I guess maybe we should include that. This lot, I will call. I'm going to call it unform because deform is quite misleading, and then I'll put the whole bunch into its own frame, and I am going to call that Mobius twist. I'm aware there ought to be an umlaut in Mobius. I'm sorry, Germany. I'm sorry. And yeah, that's the Mobius twist. Hospital twist. Why hospital twist? Well, I posted this to Reddit a few months ago, and the feedback I received, I mean, it was just so warm and encouraging, and I was inspired. What can I say? Let's disconnect the Mobius twist, and let's build the hospital twist up here. Let's get the spline parameter again. And once again, we'd like to map range the factor from 0 to 1 to 0 to tau. However, this time, instead of just using this, let's get the sign, the SINE, the trig sign of this value. Let's then put it through a multiply to have a bit of control. And then let's plug it into the tilt. And what do we have here? Well, if you can imagine the graph of y equals sine x applied to the twist as it goes round, at 0, it would be 0, sine of 0 is 0. At half pi, or 90 degrees, or a quarter of tau, it's 1. At pi, or half tau, or 180 degrees, it's back to 0, like here. And then at 3/4 tau, or pi and a half, or 270 degrees, it's -1, and then back to 0. So we have a kind of sine wave mapped to the twist around here in a full excursion because we're using tau. Okay, so this, if we change the multiplier here, we effectively change the amplitude. We're just multiplying the amplitude of that sine wave. To get a hospital twist, we just mix this with a tilt. So let's add a tilt just to see what it looks like. Get a math node, and let's add to it. And yeah, okay, it's doing that kind of thing. Right, set this back to 0. In order to have a donut which starts normally and does a hospital twist and ends normally again, what we need to do is coordinate a tilt, a full 0 to tau tilt, with something which will take this from 0 to a number and back again. How do we do that? Okay, what we need is, let's get a scene time node, and let's do this. Okay, I'm going to take the frame range down to 60, map range from the frame, and from 1 to, let's try and do it in 50 frames. I want to go from 0 to not tau this time, but to pi, because I'm going to use the sign of this number 2. The sign of 0 is 0, the sign of pi is 0, so this 1 to 50 will go from 0 to 1 and back to 0 if we use the sign. We can then use a multiplier to control the amplitude of the effect. So let's, I guess, start with 1. If we plug this multiply into this multiply and go back to the beginning, let's see what happens. Okay, it kind of goes there and it goes back. It goes there and it goes back. Maybe we could increase the strength of this. Going back. Okay. So if we do a tilt at the same time, we'll get a hospital twist. How do we do that? Once again, scene time, map range, the frame from, again, 1 to 50, and we want, again, 0 to tau for 1 full tilt. We put this into the add, and now that's a hospital twist. It's maybe looking a little bit kind of abrupt in the way it finishes, so I'm going to try on the tilt, instead of using linear, let's try a smoother step. Yeah, that's quite smooth. Okay, this is the basic hospital twist. There are variations. If instead of using tau here, so 1 tilt, if we use 2 tau, 2 times tau, we will get what I was calling the double hospital twist. Looks like that. Okay, let's take it back to tau. If, on the other hand, and yes, this will control the kind of, this is the strength control, so it's worth actually framing this and calling it strength. If we turn this up a bit, we'll get a more extreme hospital twist. Yes, that's an A&E twist. Back down to 2. If we instead of going from 0 to 1 back to 0, if we take a full excursion of a sine wave from 0 to tau, then we get this kind of effect, which I quite like this one too. I don't know what to call this. The outpatient, the inpatient, outpatient twist. I don't know. So there you go. There are play with the numbers, and you can do all kinds of weird stuff. It's not universally popular, but I like it. Okay, let's go back to pi here, and let's try and label this up a bit. What have we got? This business over here is the tilt. Okay, let's call it tilt. Ooh. This, how would we refer to this? Okay. I'm going to call this sine sine tau. That's not a great, doesn't tell you very much actually, but this one we'll call evolution. Okay, another quite vague name. I'm sorry, I haven't actually planned this very well, have I? Okay, and this whole lot is a hospital twist. So let's try and hit the right key, and then hospital twist. Okay, I'm using scene time nodes and map ranges to do all the animation. I appreciate this is not how everyone likes to work. If you'd like to do it more traditionally with keyframes and the graph editor and stuff, what I would strongly recommend is promote whatever value it is you want to animate to a group input. So let's say I wanted to, not that I do, but let's say I wanted to animate the 2 max on that map range. I would pull it back to here, and then in the main group I'd add another group input. I'd pull that back to the group input, and it would now be up there. And if we had the thing selected and we wanted to put a keyframe, there you go. It would all, I recommend doing this if that's how you want to work, but that's not what I want to do. So let's get rid of that. Okay, no thank you. Right, that's the hospital twist. Polygonal donuts, trinuts, hexanuts, dodecanuts, you get the idea. Okay, let's get out of our twister group. All of this has nothing to do with the twisting. This all happens on the major radius, so let's bring it back to give ourselves some space. All right, how would we turn this circle into a triangle? Well, really easy. Instead of a resolution of 128, we just give it a resolution of 3. This looks, I mean, yeah. Let's just resample it. And let's give it about, yes, let's give it precisely 128. Okay, it's getting somewhere. It's a bit blocky. Let's get a fillet curve node. And set it to poly, put up the count maybe to 4. And maybe we can increase the radius a little bit. Something like that. So there you go. It's not a bad triangle donut. But you might be wondering, how do we morph our regular circular donut into this? Well, that's also pretty easy. So let's get another curved circle. Let's put the resolution back up to 128. Let's put the radius back to 1. Plug this in instead, in here. Okay, now all we need up here is a set position. And from this resample curve, we need a sample curve node. Let's plug curve into curves. Let's get a spline parameter. Let's plug the factor into the factor, and it will, the factor is the thing that it morphs between, so it's very important to have this. It's also very important to have the same number of points, the same resolution on both curves. So 128 here, and this one resampled to 128. So now all we need is a mix vector, and let's plug the position into socket A, and let's plug the position of this, the sample curve, into socket B. Let's bring down the factor. Let's plug this into the position. And now, if we just move this factor, hey, there you go. And of course, it doesn't have to be a triangle. It can be a square or a pentagon or whatever. In fact, it doesn't. It doesn't even have to be a polygon. You can use any custom curve here. And of course, any of these can do the hospital twist or the Mobius twist or whatever as well. One quite nice thing is to kind of use a hospital twist as a transition between two different shapes. So to do that, all we need to do is coordinate this factor changing. So once again, we'd get a scene time node. We get a map range. We'd say, what was it, from 1 to 50. Going from 0, a circle, to 1, a triangle, or whatever you like. Maybe give it a bit of smoother step. And plug it into the factor. Go back to the beginning. And there you go. So, I hope... okay, well, actually, while I'm here... you know, we've got all kinds of variables here, and we can animate anything we want. So, you know, for example, if we want to animate the radius while all this happens, we can do that. We can animate anything which we can control. And I hope all of this is enough to demonstrate that what we've really built here is kind of a playground. And granted, it's a playground for making really weird-looking donuts. And that is probably a more niche interest than the the Olympic event it's become in my mind while I've been making this. But still, you know, there's quite a lot here which would be applicable in other scenarios. So, yeah, I hope you've had fun, and thanks for watching. Peace.